Okay, we've done intro to estimation in regression, and now we're going to do intro to inference, statistical inference. Once again, embracing the frequentist tradition, whether it makes any sense to do so or not. Popped back up here, something we've seen in from class. This is from the Campbell causal model, the 3 rules for the rules that you're required to sort of pass through before saying that X causes Y. They're going to become relevant here as we move to subsequent regression videos. They're going to become relevant here, but they already really are. Hoop number 1 is to establish that X and Y are related, and in doing the regression, in the regression context, it's in your notes from a minute ago. Here we're saying something very specific about how X and Y are related. We're saying, as we mentioned, that they're related in a linear way. Remember, number 2 is that X does not cause Y. Restated, X comes before Y, and therefore Y can't cause X, because the future, insofar as we know it in the macro world, can't cause the past. And the last one is that XY's relationship. The relationship between X, Y is not due to a third or confounding variable. Probably going to leave that up there for a few videos, just as a backdrop and a reminder of where we're headed. Repetitive from last time, here the sample version, and here the population version of a simple bivariate regression equation. Now, if I've already lost you, go back and go back to this first one and re-look at what you need to relative to the formula for a straight line, and realize we're just adding data and so forth. The sample notation, I'm using lowercase a and b for population. Parameters, I'm using alpha and beta again. I distinguish epsilon here from e. And now we're going to make some assumptions, and we're going to do some statistical inference, which we've already done, and a context remarkably similar. And I'm actually going to require less in the way of knowing formula this time. So hang on for the following ride. Now we're going to assume the following. So you can write this down as you should have already written it down. Let me explain now what it means. This is about the error term here. So we're going to assume that E, the error, is distributed. That's what the squiggly means. So is distributed, capital N stands for the normal curve, and then open pair and closed pair, and 0 and sigma squared. In English, get ready, we're going to assume that the errors are distributed normally, and that they have a mean of 0 and a constant variance. Constant variance. Could be anything, as long as it's constant. And further, and I'm coming back, don't panic, we're going to assume that EI and XI are independent. And that's going to turn out to be related here. In the context, in real contexts, this would never be true. So we're making an assumption that is not true, and we're going to use the regression model and build on it in coming videos to begin to address failing this assumption here and what it means for causal inference. So X and Y, say X and Y's relationship is not due to a third variable. There is no third variable here, so we're going to assume it away by the third variable. The only third variable is E, and we're going to assume it away the possibility of a confounding factor here by assuming that E and X are independent of each other. I'm actually going to say that E and X are uncorrelated with each other, but I like independent better because that's the formal assumption. This should give you a flavor about what E is. It's everything else that explains Y. It's everything else that explains Y, unmeasured, put together. And so what these assumptions then are saying is that everything else that affects Y sort of cancels out. It turns out to have a mean of 0. And it has a constant variance across, E does, across from the beginning of the line to the end of the line. This scatters inside a constant band. And by saying E and I and XI are independent, we're saying that everything else that affects Y is uncorrelated with x, and therefore couldn't confound our causal inference, right? Our causal inference. Even though, trust me, I know that what we're saying here is not true. It is the assumption that underlies ordinary least squares estimations. These are in this context. Put that in your pocket for a while and be ready to revisit it. As we move over here and find that b and beta are just like x bar and mu. The sample mean, the population mean, and in this case the estimated regression coefficient of the estimated slope, little b, and its population parameter cousin, parent. Its parent, beta in the population. So I'm doing repeated sampling here. I'm going the frequentist way. I'm doing repeated sampling, and you've seen something like this, and maybe you need to go back to that video or come to ask me in class to go through this again. So what I'm plotting here, just in theory, is the number of b coefficients that I come up with when I take another sample. And just for grins, let's say n is 1,000. That sample size 1,000. So I draw a sample of 1,000, and I run the OLS routine. And in R, you just say LM for linear model, and it just pops right up, fits a line to the data points. So once I've done that, we'll do this in class. Pull 1,000, find a B. Pull 1,000, find another B. Pull 1,000, all at random, simple random, find another B. And we could build in a more sophisticated probability sample than random sampling, but we're not going to do that in this class. Pull another, do that 1,000,000 times. And then, so we're looking at the relative frequencies of observing sample B's here. So this one is this spot's the most frequently observed. And we're going to say that that distribution is T, students T, remembering from earlier. And as was the case with students T, when you're dealing with a sample mean and a population mean, students T becomes Z. It becomes normal as n goes up. Central limit theorem is as hard at work here as it was in earlier problems. And you've seen it work by now in the lab. I call it the lab, in the class on your computer. You've seen it work, you know it works. So I'm talking about grabbing 1,000 over and over again with replacement, and they're going to stack up like this. B's going to have rare birds out here and rare birds out here, and one more time you're going to know that the area under the curve and use the area under the curve to say something not about causal inference but statistical inference about the population parameter beta. So we're going to go, I'm going to define T is equal to B minus B over SE B. SE stands for standard error. We're not going to worry about the formula. I hear clapping in a completely empty house. Your voices. So we're not going to worry about the formula because conceptually you now need to have grasped what a standard error of a test statistic is. And you've seen formula for more simplistic statistics, so we're just doing the same thing. We're calculating a T for B, right? In theory, in repeated sampling over and over and over. And so there we've got it. Now we can do a hypothesis test. And a lot of times, for the slope of a line, we're going to have a ready-made hypothesis. That is that B is equal to 0. Excuse me, that beta is equal to 0. So our null hypothesis, in this case, and our alternative hypothesis we'll make it two-sided. That's stupid. You should know how things are related before you run a regression. You should know whether it's positive or negative. It should always be a one-tailed test. But we'll start here and pretend that we don't know anything. And so we're going to assume that in the regression, the slope of the line in the population is not positive it's not negative, it's completely zero. So we're assuming as a null model, as a null hypothesis, that, and if we assume that, then this guy goes away, right? B minus 0 is B. T is the ratio of the estimated coefficient, the estimated slope B, to its standard error. Boy, I need to write that down. T is the ratio of the estimated coefficient, or slope, to its estimated standard error, SE. B, and just like before, there's a rule of thumb. So I've got a T of about equal to 2. Or absolute value of T, put that. If it's about 2, so put the absolute value brackets around T and not 2. So if it's about equal to 2, then you're 95% confident, right? And there will be associated with every T a p-value. And it's that dude on the printout, p-value, in the frequentist R.A. Fisher tradition that you would, if you didn't know better, now you will look at the p-value and say, I have either a statistically significant by social science norms result, or I have a statistically insignificant result. If the p-value is less than 0.05, the traditional conclusion would be that there seems to be evidence here for a relationship between X and Y crossed through hoop number 1 in the population. So T's here are just like they were before. I'm not going to belabor this on the video. Might need to in the follow-up in class, but let's go ahead and do this. So something about equal to 2 or greater is going to produce a p-value at 0.05 or lower. When n gets large, once again, z kicks in, the normal curve, and the precise value is 1.96. So for n equal to 1,000, it's going to be about 1.96. What we're talking about is going standard error this way, standard error that way, another standard error this way, another standard error that way, and getting about 95% coverage in here of an area defined across repeated samples. In our case, 1,000, 1,000, 1,000, 1,000, find a B, find a B, find a B, find a B, and you're doing statistical inference. So this is like the introduction to the causal, and for the Campbell causal use of regression models, and it is the formal introduction to statistical inference in bivariate regression. More coming.